Assalamualaikum and a very good day. Okay, before we continue, the we still at the artificial neural network, but before we going further to continue this topic, artificial neural network, I would like to give some feedback on the group task that I give to all of you, as well as try to give a feedback from the question you ask, which is related to the feedback from or response from the previous lecture that I see there's a few questions there. That there's a few students ask about the 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 doubt that you face when you learned the second lectures there. Okay, we start with your assignments. Okay, again, this is the one that I give you, the network that I give to you, which is a little bit different from the example that I give from the previous lecture. Okay, but it's actually the same ANN, which is considered as multi-layer perceptron. Okay, because you have a hidden layer there, so that's why any network which have a hidden layer, it's under category of MLP. Okay, MLP, which is a multi-layer perceptrons. And again, this is the same version, is the same type as the one that I give in lecture, because it is called as a one hidden layer neural network, or you can also call as a two layers neural network. Okay, because why two? Because I think this one in the previous, I think the first slide, you can refer to the first slide under the multi-layer perceptron, because you have two layer which consists of neurons, which is the hidden layer and the output layer. So that's why they call, also the name for this one is a two layers neural network, or you can also call as a one hidden layer neural networks. So the difference between this one and the one that I explained in the previous lecture is that the number of neuron, because this one you have at the hidden neuron, you at the hidden layer you have 4 neuron, at the output layer you only have 1 neuron. However, in my and this one also you have a 3 input or 3 attributes that fit into this network. But the one that I explained before, you have only 2 inputs, 2 neuron at the hidden layer and 2 neuron at the output layer. But still you have a 3-layer version, or the same name, or we can say that it's the same name, means that the one that I explained is also called as a 2-layer neural network, and this one is also called as a 2 layers neural network, but the different number of neurons inside that each and every layers there. Okay, but at the end, if you derive this thing, you should get the same algorithms, means that the same algorithm that, or the same pseudocode that I explained here. Okay, this one. Okay, so doesn't matter if we change the number of neuron, you should get this general step or general process. Okay, you should not get other different things there. Okay, because the number of layer is same, the difference is number of neuron, so you should get this general step. Even if I give you some problem where you have more than one hidden layer, actually it's just some adjustment at this step number 5 here, because now you have more and more hidden layer. But because I give you some tasks where the number of layers is similar to the number of layer that I give before in the simple examples there, so you should get the exact equation and exact step similar to this step. That's why we call this one as a general process there. Okay, I find out that there's a few group. Okay, I want to discuss on this. Okay, I think there are three groups try to explain or try to put effort on how actually from your variables and all your variables, how you convert it into metric version, and then from the metric version you convert into vector before you declare the operations there. But I think there's a two groups skip this step, meaning that they just skip and they just conclude on from their finding. Okay, from their finding, then they can go skip this step, and then they just end up in this general step or general process. And I think there's a three group try to relate the task, the given task, and try to derive on the given task and list up all the variables before and end up with the vectors there. Okay, but I think the only one group get a correct derivation, and the other two is a little bit incorrect there. So that's why I need to explain on this, because hopefully then when I give you some improvement on that, then you can understand how actually if we change the number of neuron, or we change the architecture, we still can get the general step there. Still we can end up at this general step there. Okay. Okay, before that I would like to revise on how actually you do the notation. I don't know why some of the group use the D there. Okay, DE they call it DEDW, because in my slide I'm using del. Okay, I'm using del. Sorry. Yeah, I'm using del. Okay. Okay. I'm using del. So why you change it using D there? I think this one you learn it in foundation or matriculation, where this one is for partial derivative, while if you talk about derivative you can use D. But if you talk about the partial derivative, you need to use the del, because if you remember that if you have equation with only single variables, single variable like y equal to mx, I put it x1 plus c. So of course if you want to do derivative of this equation, you can use dy dx1. But if you talk about multivibrated equation, multivibrated equation is like m1x1 plus m2xt plus c. So you have more than two independent variables, okay, x1 and x2 at the equation. So that is where if you want to do a derivative of this kind of equation, then you need to use the del. Okay, so that one is you want to do the derivative with respect to x1. So if you want to do if you want to do the derivative with respect to x2, then del y del x2. So in our case here, because we are dealing with a multivibrated equation where you don't have the independent variables, independent variable is more than one, you have x1, x2, x3. The attribute itself is a x1, x2, x3, so it's a multivibrated function. So that's why anything related to derivative, it's actually a partial derivative of that one. Okay, if you even it's not x1, x2 and x3. Now we talk about the w. We have w11, w12, w48 and so on. So we have a lot of multivariables variation, multivariables, or the independence variable is more than one at that function. So that's why you need to use a partial symbols. So please don't make this as your habit when you want to derive the equation in neural network, because we need to use the del there, the symbol del that represent the partial derivative. And I think for this group, another thing is that about this one. Okay, about this one. Okay, it should be delta. It's a delta, should be something like this. Okay, delta E. I don't know. Maybe you don't find the equation features in PowerPoint. So that's why you cannot you don't know how to find this symbol. So that's why you just use the D there. Okay, you don't know where to find the del symbol. That's why you press with D. But make sure that during of course in exam you need to do it in hand calculation and so on, hand derivative. So you don't have problem with that. Maybe this one is because of you don't find the feature inside your PowerPoints. So then you don't know how to write that del symbol. I'm sorry, delta symbol. So that you replace with D. Okay, but that is just some small mistake, but of course don't make it as a habit. Okay, because otherwise if you derive this one, I don't know how to differentiate between this D, which is the fully derivative, and this D. Okay, because both using the symbol Z there. Okay, then don't do that. Okay. Let's go to this one. Okay, for this group, of course, I just show you the three group that try to put effort or try to do some attempt on to convert the variables, all the variable, to the metric version and to the vector version. But for this group, I think this part is incorrect. Okay, especially at this one. Okay, at this one, because this one because every point here is D1. So how you can change it into, you can represent this one as this one, and of course even if you convert into this Hadamard product, and at the end this one is not similar to the general step that I show before. Okay, so normally this one should be a dot product. Okay, it should be a dot product with W. That is the general step happen after this one. So now you are, because it might be you don't know how to make this one as the dot product, so that's why you end up with this Hadamard product here. Okay, even the Hadamard product here is wrong, because this is D1, this is D1, this is D1, and this is D1. Then you make it as this one, because this one should be something like this. It should be D1, D2, D3, D4, and then you do some Hadamard product with W1, W2, W3, W4. So that is a what elements multiplications wise multiplication operation I'm sorry, elements wise multiplication. So it should be 1 2 3 4 1 2 3 4, but this one is 1 1 1 1, so you cannot end up in this operation. It's not similar with this one. Okay, it's not similar. Okay, and then another thing is that wrong here is that from here W48, why you change it into W1? You should change it into W. Here is what? W11 2. Then you have W12. I think because the previous one we use that notation. It's not 1 2 3 4. It should be 1 2. I think this one is for it. Okay, it should be W. This is layer number 2, and then yeah, 1 1, and then 2 1, W21, W31, W41. Okay, because you have at the output layer you have only one layer, which is we have neuron number 1, and then this one you have number 1, number 2, number 3, number 4. So this one is 1 1, this one is 2 1, this is 3 1, this is 4 1. So this is where you need to convert this one into this version. It's not this version, this is a new version. So that's why you fail to end up with a general equation there, which is should be a dot product between your delta and your W's there. Okay. Yep, this one is the same things again, because of the I just want to highlight on this one. You use you don't use a delta there, you use a D there. Okay, this one is from other groups. Okay, this one you managed to end up with the general equations there. Okay, here is good, but at this point it's a little bit, the arrangement is not correct, because if you want to, yeah, okay, it should be something like this, because if you want to make the matrix, make sure that you follow the coordinate number, because this index will represent the coordinate number of inside the matrix there. Okay, means that W11 is mean that this W is belong to row number 1, column number 1. This one is row number 2, column number 1. This one is row number 3, column number 1. So it's not like this, it should be like this. W11, W21, W31, W41. So this should be this kind of arrangement, not this arrangement. Okay, so otherwise this operation is also wrong, because 1 times 4 cannot multiply with 1 times 1. Okay, because this one is not similar. So unless if you change into this one, it should be 4 times 1 multiply with 1 times 1. So this one is same. Then if you do the multiplication, you will get 4 times 1, which is your E there. Okay. Okay, I think this group don't skip that step that we discussed before. Yeah, this was one of the group that skipped that one. But the rest is good, means that all the step there you managed to know how to derive. But the one that you miss is that how to convert it from the equation into the general process or general procedure or general algorithms, which is in vector. But it's okay for me. Is I'm satisfied with that, because we just learn about something. You can see that the mathematician put a lot of effort in derive all this equation, and at the end they managed to end up with certain general procedure in form of vector. Then the programmer just translate it into coding, and then they can implement the neural network. But that's why I ask you to derive this, so you appreciate the mathematician in creating all the formula for neural networks. And also you need to appreciate the MATLAB of doing the given task. Means that you give a very complicated example, then you ask the MATLAB to do, and MATLAB can do it very well. And of course, if you don't have a MATLAB, you cannot you cannot just depend on your hand calculation, because it will take a lot of time to generate the fit the formula that can fit with your training data. So you must appreciate that. Okay, I think yep, this one is also have the similar problem where you use the D there. Make sure don't use D. Use the del there, because del is represent the partial derivative, D represent the derivative, the only derivative. Okay, because we are dealing with multivariated functions. I think this group is quite well in representing this one. Yep, yeah, this one. Okay, so the arrangement is good there. So now you have this one is the correct. So I think all students need to refer to derivation from this group, which is the one that discussed on this part lah. Because you can see that this is how the arrangement of the matrix there. So you end up with the general equation, and then again, doesn't matter how many neuron, you still have the same general algorithm or general process there. Okay, I just want to revise on this one, because I heard about this discussion going further into this definition of the how actually the training process have been done. Okay, I think this group, when they present, they said that after one epoch you will update the W. Okay, that is incorrect. Okay, because remember that when I discuss about the one that the neural network that I give in the simple examples there, I'm using the SSD. Okay, so SSD will, because my definition of E there is SSD. Okay, is SSD. So that's why if you are using the error definition as SSD, you will end up as yeah. Because I'm using the SSD, so my algorithm will end up as a stochastic gradient descent, meaning that each iteration, the W will update. The W will updated each iterations, means that one samples come in, fit into the data, doing a forward pass, and then you are doing the backward pass. Once you get the updater, you will update the W. So means each iteration I will update my W. So it's not similar with the example that you learn in Dr. Ting class, because Dr. Ting class, you can see that during the Dr. Ting class, at the beginning your E, or your in the thing they call it a cost function J, you already assign as 1/2n. Then you have the here what the F there, and then you have here is theta. Yeah, theta. Then you have the summations there, theta I xi, and then you have here is your actual y is there. So you have a summation, you have here you also n represent the total number of sample inside the training function. But my version of J, which is I call as a E there, okay, is just 1/2. Then you will have here is the as a the predicted output minus the actual output. I think you can check the slide. I forget whether this one going into that position or this one going to that position. Okay, so you can see that there is different. This is SSD, this is MSD. So that's why when Dr. Ting derived the process in regression, it end up with batch gradient descent, because at the batch gradient descent you need to apply one epoch. This one is meaning one epoch. One epoch is meaning after you complete process the whole data set. If your data set is 100 sample, you do the iteration 100 times, you get the average you get the average error there, you get the average output there, and then you minus with the actual output, then you get the from there you will get the average error. That average error will become the cost function. While the SSD, each time you pass a single samples, then you get the error. Okay, the error is based on single samples, while this one the error is based on the average error happen at 100 sample inside your training data, or it's mean by one epoch. So that's why in this problem it will update the W after one epoch, which is 100 samples. For example, this is just an example. Let's say I have 100 sample or 100 samples of data, training data. But if I apply SSD on the same training data set, which is consists of 100 sample, for this one, W is update after one iteration, which is one samples of 100. But one epoch for this one, or in other words, one epoch, it will make the W have been updated with 100 times. But for this approach, one epoch you only update W one times only. Okay, so I hope it will make you clear about that. So another type which is called as mini batch. Okay, the one that I'm sorry. Okay, this is stochastic gradient descent. The one in under the example of Dr. Ting is batch gradient descent. There's another version is called as mini batch gradient descent, which is a mix or is a fusion between the stochastic gradient descent and batch gradient descent. So if you have, let's say this is your data set, training data set. Okay, you have 100 samples. Then I set my my batch size into 20 sample per batch. So then I will have 5 batch there. And then for mini batch gradient descent, what actually have been done there is that the W will update after they finish training this mini batch size of data. Means that for this case, because I have 5 batch, means that 20 samples 20 samples per batch, per mini batch. Okay, for mini batch. So if you talk about one approach of this, if you, let's say your algorithm apply a mini batch gradient descent, one approach, what is the meaning by one approach? Again, the one approach is similar, doesn't matter which version. One approach mean after you complete training or processing the whole training data set. It means that once you arrive at the hundredth sample number 100 inside your training data, which is the last samples, then that is one approach. From 1 to 100 fully complete process, that is one approach. But the difference is that for stochastic gradient descent, one approach you have 100 iteration, and each iteration you will update the W. That means you will update 100 times after one approach. But for batch gradient descent, you will do iteration 100 times because of you have 100 samples, but you only update the W after you process, after you execute 100 iterations there. So means that one approach you only update the W one time. But for this case, which is a mini batch gradient descent, the one that if I separate one mini batch, 20 sample per mini batch, so I will have end up with the total up to 5 batch here. So each batch here is small mini batch here. After you finish complete the process, then you will update the W. Means that one approach for mini batch gradient descent for this case is for this case. For the other case is depend on the mini batch size. Okay, but this one, because our mini batch size is 20 samples per mini batch, so that's why one approach you will update the W 5 times only. Because once you complete this one, you will get the average error of this batch only. Once you get the average error or the average cost value there, you will update your W. Then you proceed with the second batch. You find the average error there. Once you get the average error, you update your W. So, and then same go to this one. So that's why this one is similar, almost is a combination between stochastic gradient descent and batch gradient descent, because it still proceed the batch per batch error, but now you are separated into small batch. So each time you complete this small batch, you will update your W. So later you will see that this is the popular methods in updating the W, because I think later when we learn the deep learning, especially the convolutional neural network, you will see that they will use the convolutional neural network use this kind of mechanism, which is a mini batch gradient descent.